These are the answers to the AP Chemistry packet that is entitled Unit 4, Summative Assessment Practice. On this slide, you can see Unit 4 at a glance. Unit 4 is entitled Chemical Reactions. In this video, I will present practice problems that cover all of the topics in Unit 4. This video should help you to prepare for the Unit 4 Summative Assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you will see on the AP Chemistry free response section. Show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Pay attention to significant figures. Number 1, a student performs an experiment in which a sample of a metal oxide is added to a clean, dry crucible. The crucible is heated strongly with a Bunsen burner for several minutes. Data from the experiment is shown in the table below. Assume that the change in mass that occurs during the heating process is the result of oxygen gas escaping from the crucible as represented by the process shown above. In part A of this question, it says, based on the information in the data table, calculate the number of moles of oxygen that is released from the crucible during this experiment. So the mass of the crucible and the metal oxide sample before heating is 26.047 grams, and the mass of the crucible and contents after heating is 25.940 grams. So that difference in mass represents the mass of oxygen released during the experiment, and that is 0.107 grams of oxygen gas. Let's convert that to moles. So the periodic table can tell us that 1 mole of O2 weighs 32 grams, and we have 3 significant figures, so 0.107 divided by 32, there's our unrounded answer. Rounding off to 3 significant figures, that would be 0.00334 moles of oxygen, or you could write that as 3.34 times 10 to the negative 3 moles of oxygen. All right, moving on to part B of this question. It says the substance remaining in the crucible at the end of the experiment is a pure sample of a metal. The amount of metal present in the crucible is equal to 0.0134 moles. Based on this information and the information in the data table, calculate the molar mass of the metal and write the elemental symbol for the most likely identity of the metal. So we have the mass of the clean, dry crucible, which is 24.496 grams. And at the end of the experiment, we have the mass of the crucible and its contents, which again is going to be this pure sample of metal. That's 25.940 grams. So that difference in mass, 1.444 grams, represents the mass of metal. We were also given the number of moles. So since molar mass is grams per mole, grams divided by moles, the molar mass would be 1.444 grams divided by 0.0134 moles. And if we do that math, we get approximately 108 grams per mole. Now all we have to do is look on the periodic table to find an element that has an atomic mass or a molar mass of about 108. And so that would be silver, which has the elemental symbol Ag. All right, let's move on to part C of this question. It says, based on your answers to parts A and B, write the empirical formula of the metal oxide that was used in this experiment. So in part A, we had calculated the number of moles of oxygen gas that was released, and that was 0.00334 moles of O2. In part B, we discovered that the elemental symbol for the metal was silver, Ag, and they were giving us in part B that the number of moles of that metal was 0.0134. Now, to compare the moles of each element, we have to be careful because there is a difference between oxygen molecules and oxygen atoms. We want the ratio of silver atoms to oxygen atoms. So I'm going to multiply the answer to part A by 2. And the reason why I'm doing that is because I'd like to figure out the number of moles of individual oxygen atoms. And there are 2 moles of oxygen atoms for every 1 mole of oxygen molecules. So that number now becomes 0.00668. Again, that's moles of individual oxygen atoms. Now, to get the empirical formula of this silver oxide compound, I'm going to divide moles by moles. And since the number of moles of silver is a larger number, I'm going to do larger number divided by smaller number. That particular ratio, 0.0134 divided by 0.00668, that works out to be 2. So now I can write the empirical formula of this silver oxide compound. There are 2 moles of silver for every 1 mole of oxygen. So therefore, the empirical formula would be Ag2O for this silver oxide compound. In part D of this question, it says, based on your answers to parts B and C, write the balanced chemical equation for the process described above. So we know that the formula of the metal oxide is Ag2O. We know that the metal is silver. That would just be Ag by itself. And then we also know that oxygen gas was released during the heating process. And we write oxygen gas as O2. So therefore, the balanced chemical equation, I need 2 oxygens on the left, and now I need 4 silvers on the right. So there is my balanced equation with coefficients from left to right, 2, 4, and 1. Okay, in part E of this question, it says, is the process represented by the equation shown above classified as a physical change or a chemical change? Justify your answer. Well, earlier in a previous video for Unit 4, talking about physical and chemical changes, which is topics 4.1 and 4.4, you can see on this slide examples of physical changes, so change in phase, separating a mixture where no new substances are formed, and then examples of chemical changes where a new substance is formed or possibly a precipitate or the formation of a gas. So we are clearly forming a new substance with a different chemical composition in this process. So this is a chemical change. We start with silver oxide and new substances are formed. Silver and oxygen have a different chemical composition than the original substance. Silver oxide is not simply a mixture of silver and oxygen. Silver oxide is a compound. Chemical bonds between silver and oxygen are broken in this process. This is definitely a chemical change. Now, let's take a look at part F of this question. In part F, it says, the student determined that the solid metal conducts electricity. Explain this observation. Your explanation should refer to the presence or absence of charged particles in the sample and whether or not the charged particles can move or flow freely. Now, in my earlier video that talked about topic 4.2, net ionic equations, I had presented this information, which you can see on this slide. The ability of a metal to conduct electricity can be explained by the information in topic 2.4 of the AP Chemistry curriculum. Topic 2.4, Structure of Metals and Alloys, includes the following essential knowledge statement. Metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons, that is, a sea of electrons. And so the answer to part F is silver is a metallic solid. Metals are good conductors of electricity because there are valence electrons, charged particles, that are able to move and flow throughout the entire crystal lattice. And then the last part of this question, part G, the student determined that the solid metal oxide does not conduct electricity. explain this observation. Again, referring to the presence or absence of charged particles in the sample and whether or not the charged particles can move or flow freely. So silver oxide is an example of an ionic solid. Here you're looking at the model for sodium chloride. And so it's a similar thing we've talked about in an earlier video where, yes, there are charged particles, but they are not able to move and flow freely. So correct answer to letter G of this question is that silver oxide is an example of an ionic solid. And while there are positive silver ions and negative oxide ions present, they are held in fixed positions in a rigid crystal lattice. And since the ions, charged particles, are not free to move and flow, the solid does not conduct electricity. Question 2. Each of the following solutes can be dissolved in water to form an aqueous solution. Write a balanced chemical equation that represents what happens to the solute particles when the solute is dissolved in water. So we have 3 examples of solutes. We have ammonium sulfate, methanol, and aluminum nitrate. So our first example is ammonium sulfate. Ammonium sulfate contains the polyatomic ions ammonium, which is NH4 plus 1, and sulfate, which is SO4 2-. So there are 2 ammonium ions for every 1 sulfate ion. On the left, we'll write the chemical formula for ammonium sulfate, and on the right, we'll write the aqueous ions with their charges. Again, 2 ammonium ions for every 1 sulfate ion. Now, you don't have to put the symbols for phases of matter, such as S or L or AQ, but I'm going to go ahead and include them just to be complete. All right, our next example is liquid methanol. You may recall from an earlier video where I talked about electrolytes and non-electrolytes that methanol is a non-electrolyte. It is a covalent molecular substance. It does not break up into ions. So therefore, I would write liquid methanol and then aqueous methanol, but I leave it as a neutral compound. I don't split it up into ions. It remains as a molecule. And then our last example in this question is aluminum nitrate. So that consists of the monoatomic ion aluminum, which has a charge of 3+, and then the nitrate ion, which is NO3-. So there are 3 nitrate ions for every 1 aluminum ion. So I have aluminum nitrate's formula on the left, and on the right I have the aqueous ions with the appropriate charges. So ammonium sulfate is an electrolyte and splits up into ions. Aluminum nitrate is an electrolyte and splits up into ions, but methanol is a non-electrolyte and it does not split up into ions. It remains as molecules. Question 3. An experiment is performed to determine the percentage of copper by mass in a brass alloy containing a mixture of copper and zinc. A sample of the brass alloy is dissolved completely in nitric acid, HNO3, forming the aqueous ions Cu2+ and Zn2+. Data from the experiment is shown below. Part A, calculate the number of moles of nitric acid, HNO3, that is added to the brass alloy in this experiment. Now it says that the molarity of the nitric acid solution is 6.00 moles per liter. So capital M is moles per liter. We are given the volume of the nitric acid solution, which is 20.0 milliliters. We're going to convert milliliters into liters. So times 1 liter over 1,000 milliliters. And then we use 6.00 moles per liter as a conversion factor to go from liters to moles. So if we do this math, 20 divided by 1,000 times 6, again that would be 3 sig figs in our answer, 0.120 moles of nitric acid is added to the brass alloy in this experiment. In part B, distilled water is added to the reaction mixture, increasing the volume of the solution to 250.0 milliliters. It is determined that the concentration of copper ions in the solution is equal to 0.0548 moles per liter. Calculate the number of moles of copper that is present in the brass alloy sample. Again, molarity is given to us in the problem. The concentration of copper ions, 0.0548 moles per liter. So we'll start with the volume of the solution, 250.0 milliliters. We'll convert milliliters into liters, so times 1 liter over 1,000 milliliters. We'll use 0.0548 moles of copper ions per liter. If we do this math, 250 divided by 1,000 times 0.0548, round off to 3 significant figures, because the molarity has 3 significant figures. So 0.0137 moles of copper ions. Now, if you look closely, it says calculate the number of moles of copper solid. And so you might wonder, is there a difference between the copper ions and solid copper? Well, the brass alloy does contain a mixture of solid copper and solid zinc. But once that is added to the solution of nitric acid, it dissolves, forming the aqueous ions, copper and zinc. So the number of moles of copper solid is equal to the number of moles of copper ions. So the correct answer to part B is 0.0137, and again, that would be moles of solid copper that is present in the brass alloy sample. Part C, the reaction between copper and nitric acid is represented by the equation shown above. Using the balanced equation and your answers to parts A and B, determine which reactant is the limiting reactant in this experiment. Justify your answer. Your justification should include a comparison between the amount that is needed and the amount that is available. So earlier we had calculated in part A that there was 0.120 moles of nitric acid that was used in this experiment. If we use the stoichiometry, the coefficients, we can convert moles of nitric acid into moles of copper. In part B, we determined that it was 0.0137 moles of copper in the brass alloy. Again, we can use stoichiometry to convert moles of copper into moles of nitric acid. So it's going to be that 1:4 ratio that we see in the coefficients. So when I do this conversion from moles of nitric acid to moles of copper, I'll be dividing by 4, because there's 1 mole of copper for every 4 moles of nitric acid. And then when I do the conversion from moles of copper to moles of nitric acid, I'll be multiplying by 4. 4 moles of nitric acid for every 1 mole of copper. And now when I do this math and I get 2 different answers, again, it says your justification should include a comparison between the amount that is needed and the amount that is available. So 0.0300 moles of copper is needed to react with the nitric acid. But since only 0.0137 moles of copper is available, there is not enough copper available to react completely with all of the nitric acid. So that makes copper the limiting reactant. And if we go the other way, 0.0548 moles of nitric acid is needed to react with all of the copper, and we have an excess amount. We have 0.120 moles of nitric acid that was available in this experiment, so we have more than enough nitric acid available. That makes nitric acid the excess reactant. Again, copper is the limiting reactant. Part D. Calculate the percent of copper by mass in the 1.25 gram brass sample. So what percentage of copper is there in this alloy, this brass alloy, by mass? Earlier, we had calculated that there was 0.0137 moles of copper present in the alloy. We're going to use the periodic table to go from moles to grams. So on the periodic table, the molar mass of copper is 63.55, and this will give us the mass of copper in the brass sample, 0.870635, so 0.8706, just to round that off a little bit, divided by the mass of the alloy, which contains both copper and zinc, and then times 100 to convert that into a mass percent, and we get 69.7% copper by mass in this alloy. All right, moving on to part E. It says the reaction between copper and nitric acid is an oxidation-reduction reaction. Fill in the missing information below in order to identify the element that is oxidized and the element that is reduced. So let's assign oxidation numbers to each element on each side of this chemical equation. So since copper is an element, then the oxidation number of copper would be 0 on the left. Nitric acid exists as H plus ions and NO3 minus ions. So hydrogen would be +1. And within the nitrate ion, oxygen is -2. And if we look at the oxidation number of nitrogen within nitrate, it's going to be +5. And that's because there are 3 oxygens. They are each worth -2. That would be -6 total. And since the overall charge on nitrate is -1, that makes nitrogen +5. On the other side of the equation, now we have copper ions. So there are 2 nitrate ions for every 1 copper. Again, copper would be +2. And moving on to the other members of the products, we have water and we have nitrogen dioxide. So for the water, that would be H is +1, oxygen's -2, and then within that nitrogen dioxide molecule, NO2, if oxygen is -2 and there are 2 of them, that's -4, that makes the oxidation number of nitrogen within the NO2 +4. So now that we have assigned oxidation numbers for the elements on both sides of the equation, let's see what's changing. So copper is changing from 0 to +2. Nitrogen is changing from +5 to +4. Remember that if the oxidation number increases, the element is oxidized, and if the oxidation number decreases, the element is reduced. So copper is being oxidized from 0 to +2. Nitrogen is being reduced from +5 to +4. Now, just to clarify, I know that there are nitrate ions, NO3 minus, on both sides of the equation. Let me go ahead and focus on what would happen if we wrote the net ionic equation for this reaction. So copper reacting with a strong acid, nitric acid is a strong acid, it completely splits up into H plus and NO3 minus. So 4H plus and 4NO3 minus. Copper nitrate would split up into copper ions, Cu2 plus, and then 2 nitrate ions. And then we have water and NO2. So I can cross off the 2 nitrate ions on the right, and I can cross off 2 of the nitrate ions on the left. And when I do that, now my net ionic equation looks like the following. So we have copper 4H plus, 2 NO3 minus, and we have copper 2 plus, and water, and nitrogen dioxide. So again, just to remind you about what's changing, copper is being oxidized from 0 to 2 plus, and nitrogen is being reduced from +5 to +4. Question 4 is describing a precipitation reaction. It says when solutions of sodium phosphate, Na3PO4, and magnesium nitrate, Mg, parentheses around the NO3, taken twice, are combined together, a precipitate is formed. Part A, write the balanced molecular equation for the reaction. And even though it says you do not need to include symbols for phases of matter, such as S or AQ, I'm going to go ahead and include them in the video just to be complete. So our formula for sodium phosphate is Na3PO4. The charge on sodium is +1. The charge on phosphate is 3-, so we need 3 sodiums for every 1 phosphate in that formula. And then magnesium nitrate contains magnesium, which is 2+, and nitrate, which is NO3 minus 1. So there are 2 nitrate ions for every 1 magnesium ion. As far as the products are concerned, sodium's new partner is the nitrate ion, and the formula would be NaNO3. Magnesium's new partner is the phosphate ion. So for magnesium phosphate, since the charges on magnesium and phosphate are +2 and -3, respectively, we need 3 magnesium ions for every 2 phosphate ions. So now we have to balance the overall equation. I would need 3 magnesium ions on the left and 2 phosphate ions on the left. So we can take care of it like this. And now I need 6 sodiums and 6 nitrate ions on the right. So our coefficients from left to right would be 2, 3, 6, and 1. And so there are the formulas of the reactants and the products. I put question marks if I'm going to go ahead and write either AQ or S for aqueous or solid. I have to remember those snap ions. Since sodium and nitrate are members of the soluble snap ions, that means that sodium nitrate would be soluble, or AQ, aqueous, and then my precipitate would be the magnesium phosphate. So part B, what is the chemical formula of the precipitate? Mg3, parentheses PO4, 2, and then write the balanced net ionic equation for this precipitation reaction. So we can split up the reactants, and we can split up the sodium nitrate in the products. We're not going to split up the magnesium phosphate because that is an insoluble precipitate. So when I split up sodium phosphate with that 2 in front as a coefficient, that would be 6 sodium ions and 2 phosphate ions. When I split up the magnesium nitrate, there's a 3 in front. That would be 3 magnesium ions and 6 nitrate ions. And when I split up the sodium nitrate on the right, that would be with that 6 in front, 6 sodium ions and 6 nitrate ions. Again, I'm not going to split up the formula for the magnesium phosphate, the precipitate. Well, if you examine the left and the right of this complete ionic equation, we can cross off our spectator ions, which would be sodium and nitrate. And now what remains would be the net ionic equation. So 2 phosphate ions reacting with 3 magnesium ions to produce magnesium phosphate. Question 5 is another example of a precipitation reaction. This time we're going to be combining solutions of potassium hydroxide and nickel Roman numeral 2 chloride. So potassium hydroxide contains the potassium ion, which is +1, and the hydroxide ion, which is -1. And then for nickel chloride, again, that would be 2 chlorides for every 1 nickel, which carries a 2+ charge. Potassium's new partner is the chloride ion, so just KCl, +1, -1. And nickel's new partner is the hydroxide ion, so we need 2 hydroxides for every 1 nickel. To balance the equation, we're going to need 2 hydroxides on the left, and we're going to need 2 potassium ions and 2 chloride ions on the right. So our coefficients from left to right are 2, 1, 2, and 1 in the molecular equation. So there are the chemical formulas. If we're not sure which one of these products is the precipitate, remember that the snap ions include potassium. So potassium chloride is soluble and will be aqueous. That means that our precipitate is the nickel hydroxide. So part B, what is the chemical formula of the precipitate? That would be nickel hydroxide, Ni, parentheses OH2. And then let's split up the reactants, and let's split up the potassium chloride in the products. We're not going to split up the nickel hydroxide, the precipitate. So here's our complete ionic equation. 2 KOH, that means 2 potassium ions and 2 hydroxide ions. NiCl2, 1 nickel ion and 2 chloride ions. 2 KCl, 2 potassium ions, 2 chloride ions. And then again, our nickel hydroxide precipitate. When we examine the left and the right of the equation, we can cross off our spectator ions, which would be potassium and chloride. And then what remains is our net ionic equation. So 2 hydroxide ions react with 1 nickel 2+ ion to produce the solid nickel hydroxide precipitate. Question 6 involves a particle representation of the reaction between fluorine and chlorine. So we have a particle diagram representing a mixture of fluorine and chlorine in the reaction vessel in the box on the left. And then we have to draw in the box on the right a particle diagram representing the contents of the reaction vessel at the completion of the reaction. So let's keep track. We have 3 molecules of fluorine reacting with 1 molecule of chlorine, and that would produce 2 molecules of ClF3. Let's do that again. 3 molecules of fluorine reacting with 1 molecule of chlorine to produce 2 molecules of ClF3. Now the only molecules that are left in the reactant mixture that have not been accounted for are 2 additional molecules of chlorine that are in excess or extra left over at the end. So now that particle diagram is complete. Question 7 is a limiting reactant problem. We are given a balanced chemical equation between C5H8O, which is called cyclopentanone, and oxygen, O2. In a certain experiment, a mixture of 15 grams of cyclopentanone and 35 grams of oxygen is added to a previously evacuated reaction vessel. The mixture is sparked and the reaction described by the equation above occurs until one of the reactants is completely consumed. Part A, determine the identity of the limiting reactant in this experiment. Justify your choice. Include both words and calculations in your justification. So there are 2 strategies to determine the identity of the limiting reactant. One strategy is to compare how much reactant is needed with how much reactant is available. So let's try that strategy first. The molar mass of cyclopentanone is 84.114 grams per mole, and the molar mass of O2 is 32.00 grams per mole. We have 15 grams of cyclopentanone, so first I will convert from grams to moles of cyclopentanone, then using the coefficients from the balanced chemical equation, we'll convert from moles of cyclopentanone to moles of oxygen, and then to grams of oxygen using the molar mass. And if we do this math, we get 37.09 grams of O2 is needed to react with all of the cyclopentanone. And if we go the other way, starting with 35 grams of O2, again, first grams to moles, then from moles of O2 to moles of cyclopentanone, and then finally to grams of that chemical, we get 14.15 grams of cyclopentanone is needed. Now that we've done the stoichiometry calculations to convert grams of each reactant into the other reactant, let's compare how much is needed with how much is available. So I start with 35 grams of O2, but 37 grams of O2 is needed, so there is not enough O2 available to react completely with all of the cyclopentanone. So O2 is the limiting reactant. And if we go the other way, I have 15 grams of cyclopentanone available, but only 14.15 grams is needed. So there is extra cyclopentanone available. That makes the cyclopentanone the excess reactant, and O2 is the limiting reactant. Again, there's more O2 needed than is available, so I don't have enough O2 available. That's what makes O2 the limiting reactant. The other strategy is to convert each reactant into product and see which one is a smaller amount, or which one produces a smaller amount of product. So I'll convert each of them into one of the products. I'll pick CO2. So CO2 has a molar mass of 44.01 grams per mole. So first, grams to moles of cyclopentanone, and then from moles of cyclopentanone to moles of CO2 using the coefficients, and then using the molar mass of CO2, I convert to grams. So that number is 39.24 grams of CO2. Let's start with the other reactant. First grams to moles, then from moles of O2 to moles of CO2, and then to grams of CO2, and I get a different value. When comparing these two values, for grams of CO2, it is the smaller number that I'm focusing on. So since 37 is smaller than 39, that means that O2 is the limiting reactant because it leads to a smaller amount of product in our stoichiometry calculations. The theoretical yield of product always comes from the limiting reactant. So that 37.03 grams is a smaller value than 39.24. So I focus on that, and that tells me that O2 is the limiting reactant. It leads to a smaller amount of product. In part B, calculate the theoretical yield of CO2 for this experiment. Well, we just did that. It's going to be 37 grams of CO2. Rounding off to 2 sig figs, my theoretical yield of CO2 is 37 grams. All right, let's move on to question 8, which is a titration experiment. Hydrofluoric acid reacts with potassium hydroxide according to the equation above. A student performs a titration experiment in order to determine the concentration of HF in a hydrofluoric acid solution. The student prepares a clean burette by filling it with a standard solution of 0.725 molar potassium hydroxide. A sample of 50.0 milliliters of aqueous HF is measured in a graduated cylinder and transferred to an Erlenmeyer flask. A few drops of an acid-base indicator is added to the flask to ensure visual detection of the endpoint. The images below show close-up views of the burette containing 0.725 molar potassium hydroxide at the beginning of the titration on the left and at the endpoint on the right. So on the left, I would say that that volume reading should be somewhere between 2 and 3. Looking more closely, I would say that the bottom of the meniscus is between 2.2 and 2.3. And if I estimate it's about halfway, that would be 2.25 milliliters. That's my initial burette reading. The final burette reading at the endpoint would be somewhere between 41 and 42. And it looks like it's right on the line. The bottom of the meniscus is on the line at 41.2. So we'll call that 41.20 because we always read a burette to 2 decimal places. Each line is worth 0.1 milliliters, so we estimate to the 100th place. The difference between the initial and the final burette reading is 38.95 milliliters. So now we have the volume of 0.725 molar potassium hydroxide that was required to reach the endpoint. Part B, based on the given information and your answer to Part A, calculate the concentration in moles per liter of HF in the 50.0 milliliter sample of aqueous hydrofluoric acid. So we'll start with volume of KOH. We'll convert volume into moles. So molarity is moles over liters. So 38.95 milliliters of that KOH solution. There's 0.725 moles of KOH for every 1 liter, or 1,000 milliliters. And looking at the stoichiometry and the balanced equation, there's 1 mole of HF consumed for every 1 mole of KOH consumed in this reaction. If we do this math, we get 0.02824 moles of HF. And since the volume of the HF solution was 50.0 milliliters, we're going to do molarity as moles over liters. So 0.02824 moles of HF divided by the volume in liters. So divided by 0.0500 liters. This will give us our molarity. So if we do this math, we get 0.5648, rounding off to 3 significant figures, 0.565. And you could say capital M, or moles per liter. All right, part C of this question. The student performed a second trial of the titration, using a graduate cylinder to measure a 50.0 milliliter sample of HF, just like in trial 1. However, the student made a mistake when the HF was transferred from the graduate cylinder to the Erlenmeyer flask. A few milliliters of HF were accidentally spilled onto the laboratory counter instead of being added to the flask. The student continued with the titration procedure. Calculations were based on the assumption that the volume of HF was 50.0 milliliters. So do you predict, based on this mistake, is the calculated value for the concentration of HF in trial 2 less than, greater than, or the same as the value obtained in trial 1? Justify your answer. So because of the mistake in which a few milliliters of HF were accidentally spilled onto the laboratory counter, less than 50.0 milliliters of that aqueous hydrofluoric acid solution actually made it into the flask. So our volume of HF is less than 50 milliliters, which means if we have a smaller amount of acid, then we will need a smaller amount of base to reach the endpoint. So the volume of base required to reach the endpoint will be less than in trial 1. Here are the calculations from part B. The volume of KOH will be smaller in trial 2, and that will lead to a calculated value of HF that will be smaller, and a concentration of HF that will be smaller. So the correct answer to part C is that the calculated value for the concentration of HF in trial 2 should be less than that value obtained in trial 1. And the reason why is because the volume of the acid used is less than 50 milliliters. The number of moles used in the titration is less than in trial 1. So the amount of base needed will be too low. And the calculated value for moles of KOH and moles of HF would be too low. So the concentration of HF calculated in trial 2 will be too low, so less than the value obtained in trial 1. All right, let's take a look at question 9. In question 9, we are given an acid-base reaction, and it says to identify both sets of conjugate acid-base pairs in this reaction. So remember that an acid is a proton donor, so a substance that donates H+ ions, and a base is a proton acceptor, a substance that accepts H+ ions. So HCN is losing H+, it's donating H+. That makes HCN the acid, and its conjugate base is Cn-. The water is accepting H+. So water behaves as a base, as a proton acceptor, and then its conjugate acid would be the hydronium ion H3O+. Question 10, we have a new acid-base reaction. Again, we're going to identify both sets of conjugate acid-base pairs. Water is losing H+, so water is behaving as an acid, and its conjugate base is the hydroxide ion, OH-. The other molecule, CH3NH2, is acting as a proton acceptor, so it's a base, and its conjugate acid would be CH3NH3+. All right, moving on to question 11. It says, add the following half reactions together to produce a balanced redox equation in which the electrons are canceled out on both sides. So we have an oxidation half reaction involving the loss of 2 electrons, and we have a reduction half reaction involving the gain of 5 electrons. So the least common multiple of 2 and 5 is 10. So we can do whatever it takes to get the electrons to be canceled out on both sides. So let's multiply the oxidation half reaction by 5. And let's multiply the reduction half reaction by 2. So when we do that, our coefficients in the oxidation half reaction will be 5, 10 and 10. And the coefficients in our reduction half reaction will be 10, 2, 16, 2, and 8. Now let's add the two half reactions together. Notice that the electrons are going to cancel out on opposite sides. And this is what we get. So 5 ions of C2O4, 2 minus, 2 ions of MnO4 minus, and then 16 H plus ions. That's a total charge on the left of positive 4. And on the right, we have 10 molecules of CO2, 2 Mn, or manganese, 2 plus ions, and 8 molecules of water. That's a total charge of positive 4. So the atoms and the total charge are balanced. So this is our overall balanced redox equation. Okay, let's move on to question 12. Consider the balanced equation shown above. Assign oxidation numbers to each element on the left side of the equation. So we'll start with NO2 minus. Oxygen will be -2, and we have 2 of them, so that's -4. And in order for the sum of the oxidation numbers to equal the charge on this ion, that makes the oxidation number of nitrogen +3. Then we have aluminum, which exists as an element on the left. That's going to be 0. Hydrogen is +1 in water and in the hydroxide ion, and oxygen is -2. So +1 for hydrogen, -2 for oxygen. Now, let's assign oxidation numbers to each element on the right side of the equation. So NH3, that's ammonia, that's a molecule. The sum of the oxidation numbers would equal 0 in that compound. Each hydrogen is worth +1, and we have 3 of them. So that makes the nitrogen -3 in the NH3 compound, ammonia. Aluminum is part of a polyatomic ion, which has the formula Al and then OH inside parentheses. We have 4 of them, and the overall charge is -1. So OH is hydroxide, which is worth -1. We have 4 hydroxides, that would be -4. That makes the aluminum +3 in that particular polyatomic ion. Hydrogen should be +1. Oxygen should be -2. So now we have assigned the oxidation numbers to each element on both sides of the equation. Remember that if an oxidation number increases, the element is oxidized, and if it decreases, it is reduced. So what's changing? Well, nitrogen is going from +3 to -3. So nitrogen is being reduced from +3 to -3. And then aluminum is changing from 0 to +3. Aluminum is being oxidized from 0 to +3. So in part C, aluminum is being oxidized from 0 to +3. Nitrogen is being reduced from +3 to -3. All right, well, that was the end of the Unit 4 Summative Assessment Practice. I hope that these answers and explanations were helpful. Thanks for watching.